All right, guys. So today and tomorrow we're going to kind of finish up simplifying radicals by talking about how we add and subtract them. And if you are keeping up with your table of contents, I think I put 83, 84, but I'm going to add 2 pages of practice on, like just some examples for you guys to try. So I changed that to 86 just in case. Also, back on this page here, we got a couple of things to fill in. So we talked last week about multiplying and dividing roots. We also talked about this thing with denominators where mathematicians are not cool with roots on the bottom, so we need to rationalize, which is just code word for get roots out of the denominator. Out of denominator. So that was another thing we should add there. Okay, so this week, beginning of the week, we're going to talk about how we add and subtract roots. And I think it's actually easier than multiplying and dividing. It's a little less simplifying involved. You still have to simplify, but I think it's, I don't know, because you know how to combine like terms, it's a lot like that. So when we are adding or subtracting roots, we can only add or subtract like radicals, which means that they have the same index. So they have like the same little baby number, so it's got to be like a cube root with a cube root. And they have to have the same inside number. So like these numbers inside here have to be the same. Now you can just say inside number, but that does have a special name. It's called the radicand. But like me and vocab are not always BFFs. So I understand if you just call it the inside number or under the root. Okay, so got that. So jumping now to page 84, which we were working on last week. And here we really just did example 2 and 3 and then some of this rationalizing stuff down here. So we're actually going to go back and look at example 1. Okay, we're definitely going to skip 3. And maybe you can see why, like it doesn't have a rooty in it like all the other ones do. And so at the top here it says a radical expression can be added or subtracted as long as they are like radicals. Simplify unlike radicals first to see if they can be combined. So if they aren't alike, then we might be able to simplify them so that they do become alike. So pretty simple example on number 1. This is a full number right here, and this is another full number right there. And they are like radicals because they are both the 4th root, and they both have the same inside number of x. And so as long as it passes that little test, then really all you need to do, and let's get a little color in here maybe, is look at the numbers in front and just combine like you're combining x's. So I have -4 and -6 here for -10. And then I just bring the 4th root of x down. And that's it. So similarly on number 2, I have the 5th root, so they are the same index, and 13 and 13. And 13 is as small as it can get, and so since they're the same, we just look at the numbers out front. We got a 2 and a 5 for 7 5th roots of 13. Okay, so 3 we said we were going to skip. Number 4, they're both square roots, but this has a 5 under, and that's a 20 under. Now 5 is as small as it gets, but 20, I might be able to like birthday cake that and make it smaller. So if I take 20 and I divide 2 out, because 2 is prime, I get 10. I can divide another 2 out for 5, and then 5 is prime. So a 2 will come out of this root and smash up against the 2 that's already there. So the 7 root 5 is just coming down. But now I'm going to have a 2 smashed up against this other 2 that's coming out. So 4, because 2 times 2. And then root 5, because the 5 didn't have a buddy, so he's got to stay. And so now they actually are the same root. So that's what I mean by simplify unlike radicals, because chances are you'll be able to then add or subtract them, because now they are the same root, because they're both root 5. And so I have 7 minus 4, so 3 root 5. Okay, so similarly, if I look at number 5, I have both fourth roots, so that's a good sign, but the 162 and 32 are different. But they're both large, so I can probably birthday cake both of them. So I'm going to take the 162 and take a 2 out, so 81. I can take a 3 out, so 2, right? 21, 7, yeah, okay. Division is sometimes hard. We got lots of 3s. That's the last 3, birthday candle. Okay, so this is a fourth root. We're looking for groups of 4, so I got 1, 2, 3, 4. So a 3 will come out, and then I'll have a fourth root of 2 left. Okay, we're going to do the same thing with the 32 and birthday cake that, so I can take a 2 out, we got 16, and then 2 for 8, and then 2 for 4, 2, birthday candle. Okay, so again, a fourth root, we're looking for groups of 4, so I have 1, 2, 3, 4 2s. So a 2 can come out, and it's a negative, so -2, and then a 2 stays in. And so now my roots are the same because I have fourth root index and I have a 2 under. And so again, just paying attention to the numbers out front, we can do 3 minus 2 for 1, and you can put the 1 there or not. Oh my gosh, I'm so sorry, I'm gonna sneeze probably. Pineapple, pineapple, pineapple. Okay, it went away for now, I don't know. Anyways, you can put the 1 there or not. Either way is fine. If I sneeze, I'm sorry. Okay, 6. So if I look at the roots, they're both square roots, which is good. But this is a 5 and that's a 20. But again, 20 is pretty large. We did that one up here. Also, I can square root y to the 4th. And so like the square root of y to the 4th is just like dividing the 4 by 2. So I'll have y squared come out. But the 5 is as small as it gets, so that stays. So the 20, if you remember up here, we took a 2 out and left a 5 in, so a 5 will stay in. There's a y already out, but I can take another y out because of this y squared, and the square root of y squared is another y, so squared like that, and it's minus. Now this one is super tricky because not only does it have a root that has to be the same, but it also has to have it also has a letter, and the letter has to be the same and has to have the same power. But since all those things match up, again, I can just take a look at the coefficients. And we got 3 minus 2 for 1, y squared root 5. And again, you can put the 1 there or not. Either way is good. Okay, so that's kind of the basics of adding and subtracting. But I actually want to add something else in too. Because when we have something like this, I can't really add or subtract inside. But this is like an extension of multiplication that we were talking about last week, because if I have 2 numbers times 2 numbers, we can do FOIL, or you can set up a Punnett square if you're into that, but like I'm just going to do FOIL. So first times first would be 1 times 3, so 3. Outer, we're going to have 1 times negative root 3, and you can multiply whatever you want. It's just like the outside numbers have to multiply, and 1 times 1 is 1, and then the inside numbers multiply, and like this doesn't have an inside number, so it's really just going to look like minus root 3, because 1 times anything is itself. Okay, then we got inner, and it's going to be negative. Now the 2 and 3 I'm not going to really multiply because the 2 is inside, 3 is outside, so they're just going to like smash up. So I have 3 root 2. And then last times last. Now the 2 and the 3 are both under, so you can multiply them for 6, and then a negative times a negative is a positive. So after you kind of go through and multiply all the things, now it's a big addition problem, and so we want to look for like roots. Now they're all square roots, but this has a 3 under, can't get any smaller. This has a 2 under, can't get any smaller. And this has a 6 under, and a 6 can't get any smaller either. So I can't combine anything else, and so that is as simple as it can get, which I know is sometimes super uncomfortable that you can't like mash more numbers together, but you just can't here because they're all different. Okay, so another one like that, I can FOIL, so 2 times 4 is 8, and then we would do outer. Now this is my sloppy cube root, so it's not really a 3 outside, it's supposed to be the index, whoopsies. So the 2 and the 9 I can't actually multiply, but I can smash them up and it's negative. So 2 outside and 9. Okay, when we do inner, I can multiply the 4 by the outside 3, so we'll have negative 12 cube root 3. And then last, they're both cube roots, so I can multiply the under numbers. So 3 times 9 is 27, and then the outside number is 3, and it's negative. Okay, so once we go through and multiply, then we want to take a look and see if we can add any of these up. So, like the cube root of 9, like they're all cube roots, which is good, but 9 can't get any smaller because it just breaks up into 3 and 3, and I won't have a group of 3. The 3 can't get any smaller, it's prime. But the 27, the cube root of 27 is 3. Like 3 times 3 times 3 is 27. And that's going to be smashed up against the 3 that was already there. And so you're really going to have 8 minus 2 cube root 9 minus 12 cube root 3 minus 9, because 3 times 3 is 9. And then I can actually combine these, the 8 and the negative 9, because they don't have any roots on them. So that's negative 1, and then minus 2 cube root 9 minus 12 cube root 3 will be my final answer. So again, I know it's uncomfortable to leave like multiple numbers there, but you just can't smash any of the other ones up. Okay. Last but not least, another FOIL one like that. Now this one is unique because if you notice, like the parenthesis numbers have been completely different. These parenthesis numbers are similar, like they're both 5s and both root 7s. The only difference is that one is minus and one is plus. And when you get something like that, something interesting happens. And so that's why I wanted to do one like this. So 5 times 5, we get 25. And we do outer, so positive 5 root 7. Inner, we'd have minus 5 root 7. And then last, it'll be negative. And then root 49, because the 7s are both under. Okay, so now when I look through, these are both square roots of 7, so I can combine those, and 5 minus 5 is 0, so they just go away. And then the square root of 49 is 7, and so I'm left with the 25 minus 7 for 18, because math is hard. So the really unique thing about those, like when you have the same numbers, but one's a minus and one's a plus, is that your roots will always disappear. These sorts of pairs are called conjugate pairs, and they're super helpful for when we have to do that rationalize thing. So this is the last one I'm going to do with you, and then I'm going to give you guys some examples to try. So, as we were talking about last week, it's not cool to leave roots in the bottom, and since there is more than one number down there, it's like a binomial thing, and you can't combine them, you can't use the same method of rationalizing as we did last week. When there's just one single number down there, you can just multiply by the root. But with this one, we want to still multiply by a fraction, same thing on top and bottom, but you're going to multiply by that conjugate pair, because if I do the same numbers but different signs, I know the roots will disappear every time. So in the denominator there, we can FOIL it fully, but like the outer and inner terms will just disappear. So really you just have to do first times first, which is 1, and last times last, which is going to be negative root 9, which is 3. So your full denominator there becomes negative 2. Now on top, I have one number times two numbers, so I'm going to have to distribute that 2. And if this was like 2 numbers, then you'd have to FOIL the whole thing, but we're just going to distribute, so 2, because 2 times 1, and then plus 2 root 3. Now all these are divisible by 2, so that's kind of fun. And you can call it negative 1, because like 2 divided by negative 2 is negative 1, and then negative 1 root 3 could be your final nice answer there. Okay, so we turn the page, 85, 86, I have examples for you guys to try. So you got 4 over here, examples 1 through 4, and if you need to pause to write them down, go for it. And then on page 86, I got 4 more for you to try. So really these are the only ones you need to send me a picture of, and then we'll go over these on the next video. Good luck, guys.